Hello students. It's wonderful to have you all back. Today, we are moving into part 2 of electric fields. But before we get started, let's take a moment to review what we learned in our previous lesson. In our last class, we talked about the sources of electric charge, such as battery cells, and we also discussed electric circuits, which can be connected either in series or in parallel. The objective for today is to delve into the concept of material properties and the meter bridge. Material properties, which are the characteristics or traits of a material that define how it behaves under various conditions. These properties help determine how a material can be used in real-world applications like construction, electronics, manufacturing, or product design. Let's focus on resistivity and conductivity of materials in electricity. Resistivity is a measure of how strongly a material resists the flow of electric current. It tells us how much opposition a material offers to the movement of electrons. The unit of resistivity is ohm meter, omega m. The formula for calculating resistivity is ρ equals R multiplied by A divided by L. This means that resistivity is equal to the resistance of the material multiplied by its cross-sectional area, divided by its length. Where ρ is the resistivity, R is the resistance of the material, in ohms, omega. A is the cross-sectional area, in square meters. L is the length of the material, in meters, m. If a material has high resistivity, it means that electricity has a harder time flowing through it. Materials like rubber and glass are good examples of this. On the other hand, conductivity is a measure of how easily electric current can flow through a material. It tells us how well a material conducts electricity. Materials with high conductivity allow electric current to pass through them easily. The unit of conductivity is Siemens per meter. The formula for conductivity is conductivity equal to 1 divided by resistivity, where sigma equals the conductivity of the material, and ρ is the resistivity. This means that conductivity is the inverse of resistivity. Therefore, a material with low resistivity will have high conductivity, and vice versa. Aluminum and copper are great examples of highly conductive materials. Let's solve a basic but important problem in electricity. We are given a wire with the following properties. Resistance, R, is 5 ohms. Length, L, is 2 meters. And the cross-sectional area, A, is 0.5 times 10 to the power of negative 6 square meters. Now, we are asked to find two things. First, the resistivity of the wire. And second, the conductivity of the material. Let's begin with resistivity. The formula for resistivity, ρ, is resistance multiplied by area, divided by length. Substituting the given values. ρ equals 5 multiplied by 0.5 times 10 to the power of negative 6, divided by 2. That gives us 2.5 times 10 to the power of negative 6, divided by 2. Which equals 1.25 times 10 to the power of negative 6 ohm meters. That's the resistivity of the wire. Now, moving on to conductivity. Conductivity, represented by the Greek letter sigma, is the reciprocal of resistivity. So we calculate 1 divided by 1.25 times 10 to the power of negative 6. This gives us 0.8 times 10 to the power of 6, or 8.0 times 10 to the power of 5 Siemens per meter. And there you have it. Resistivity is 1.25 times 10 to the power of negative 6 ohm meters. And conductivity is 8.0 times 10 to the power of 5 Siemens per meter. Our next objective today is meter bridge, which is a device based on the Wheatstone bridge principle, used to determine unknown electrical resistances accurately. Let's break this down step by step. Let's look at the meter bridge diagram, which is all about finding the unknown resistance. From the diagram. So, Here's the setup. You have a known resistance, let's call it R, measured in ohms. You're trying to find an unknown resistance, which we'll call X. The total length of the wire in the meter bridge is usually 1 meter, or 100 centimeters. And K stands for the resistance per unit length of the wire, in ohms per meter, but that will cancel out in the process. Now, when the meter bridge is balanced, R1 over R2 equals L1 over L2. Since the resistance per unit length, K, is the same throughout the wire, it cancels out. So we don't need to include it in the ratio. Also remember, length 2 is equal to 100 minus length 1. So if you know the length on one side of the bridge where the galvanometer reads 0, you can easily find the other side by subtracting from 100. Let's solve an example. In a meter bridge experiment, a student connects an unknown resistance X in one gap and a 30 ohm standard resistor in the other gap. The balance point is found at 60 centimeters from point P. What is the value of the unknown resistance X? To calculate the value of the unknown resistance X, we use the principle of the meter bridge. The formula is R1 divided by R2 equals L1 divided by L2, where R2 is the known resistance, which is 30 ohms. L1 is the length from point P to the balance point, which is 60 centimeters. L2 is the remaining length from the balance point to point B, which is 100 minus 60, giving 40 centimeters. Substituting into the formula, X divided by 30 equals 60 divided by 40. Now, solve for X. Multiply both sides by 30, so X equals 60 divided by 40 times 30. That gives X equals 1.5 times 30, which equals 45 ohms. Final answer, 45 ohms. Congratulations on completing this lesson. You should be proud of yourself. Put your knowledge to the test by trying these questions. They are a great way to deepen your understanding of the topic. In today's session, we explored material properties and the meter bridge. I hope you found the class both enlightening and engaging. In our next lesson, we'll move forward with electric field, part 3. Thank you.